Today we will learn compaction test. Introduction. This laboratory test is performed to determine the relationship between the moisture content and the dry density of a soil for a specified compactive effort. The compactive effort is the amount of mechanical energy that is applied to the soil mass. Several different methods are used to compact soil in the field, and some examples include tamping, kneading, vibration, and static load compaction. This laboratory will employ the tamping or impact compaction method using the type of equipment and methodology developed by Proctor in 1933. Therefore, the test is also known as Proctor test. Two types of compaction test are routinely performed. 1. The standard Proctor test, and 2. The modified Proctor test. Each of these tests can be performed in three different methods as outlined in attached table 1. In the standard Proctor test, the soil is compacted by 5.5 lb hammer falling a distance of 1 foot into a soil filled mold. The mold is filled with 3 equal layers of soil, and each layer is subjected to 25 drops of the hammer. The modified Proctor test is identical to standard Proctor test, except it employs a 10 lb hammer falling a distance of 18 inches and uses 5 equal layers of soil instead of 3. There are two types of compaction molds used for testing. The smaller type is 4 inches in diameter and has a volume of about 1 by 30 feet cube, 944 centimeter cube, and the large type is 6 inches in diameter and has a volume of about 1 by 13.333 feet cube, 2123 centimeter cube. If the large mold is used, each soil layer must receive 56 blows instead of 25. Note: volume of 4-inch diameter mold is equal to 944 centimeter cube. Volume of 6-inch diameter mold is equal to 2123 centimeter cube. Verify these values prior to testing. Significance: mechanical compaction is one of the most common and cost-effective means of stabilizing soils. An extremely important task of geotechnical engineer is the performance and analysis of field control tests to assure that compacted fields are meeting the prescribed design specifications. Design specifications usually state the required density as a percentage of the maximum density measured in the standard laboratory test and the water content. In general, most engineering properties such as the strength, stiffness, resistance to shrinkage, and imperviousness of the soil will improve by increasing the soil density. The optimum water content is the water content that results in the greatest density for a specified compactive effort. Compacting at a water content higher than weight of the optimum water content results in a relatively dispersed soil structure, parallel particle orientations that is weaker, more ductile, less pervious, softer, more susceptible to shrinking, and less susceptible to swelling than soil compacted dry of optimum to the same density. The soil compacted lower than dry of the optimum water content typically result in a flocculated soil structure, random particle orientations that has the opposite characteristics of the soil compacted weight of the optimum water content to the same density. Equipment: molds, manual rammer, extruder, balance, drying oven, mixing pan, trowel, has 4 sieve, moisture cans, graduated cylinder, straightedge. Test procedure: 1. Depending on the type of mold you are using, obtain a sufficient quantity of air-dried soil in large mixing pan. For the 4-inch mold, take approximately 10 lbs, and for the 6-inch mold, take roughly 15 lbs. Pulverize the soil and run it through has 4 sieve. 2. Determine the weight of the soil sample as well as the weight of the compaction mold with its base without the collar by using the balance and record the weights. 3. Compute the amount of initial water to add by the following method. A. Assume water content for the first test to be 8%. B. Compute water to add from the following equation, where water to add and the soil mass are in grams. Remember that a gram of water is equal to approximately 1 millimeter of water. 4. Measure out the water, add it to the swirl, and then mix it thoroughly into the swirl using the trowel until the swirl gets a uniform color. 5. Assemble the compaction mold to the base. Place some swirl in mold and compact the swirl in the number of equal layers specified by the type of compaction method employed. The number of drops of the armor per layer is also dependent upon the type of mold used. See table. The drops should be applied at a uniform rate not exceeding around 1.5 seconds per drop, and the rammer should provide uniform coverage of the specimen surface. Try to avoid rebound of the rammer from the top of the guide sleeve. 6. The swirl should completely fill the cylinder, and the last compacted layer must extend slightly above the collar joint. If the swirl is below the collar joint at the completion of the drops, the test point must be repeated. Note: for the last layer, watch carefully and add more swirl after about 10 drops if it appears that the swirl will compacted below the collar joint. 7. Carefully remove the collar and trim off the compacted swirl so that it is completely even with the top of the mold using the trowel. Replace small bits of swirl that may fall out during the trimming process. 8. Weigh the compacted swirl while it's in the mold and to the base and record the mass. Determine the weight mass of the swirl by subtracting the weight of the mold and base. 9. Remove the swirl from the mold using a mechanical extruder and take swirl moisture content sample from the top and bottom of the specimen. Fill the moisture cans with swirl and determine the water content. 10. Place the swirl specimen in the last tray and break up the swirl until it appears visually as if it will pass through has forceps. Add 2% more water based on the original sample mass and remix as in step 4. Repeat steps 5 through 9 until, based on weight mass, a peak value is reached followed by two slightly lesser compacted swirl masses. Analysis 1. Calculate the moisture content of each compacted swirl specimen by using the average of the two water contents. 2. Compute the weight density in grams per centimeter cube of the compacted swirl sample by dividing the weight mass by the volume of the mold used. 3. Compute the dry density using the weight density and the water content determined in step 1. Use the following formula, where W is equal to moisture content in percent divided by 100 and rho is equal to weight density in grams per centimeter cube is equal to m by v. 4. Plot the dry density values on the y-axis and the moisture contents on the x-axis. Draw a smooth curve connecting the plotted points. 5. On the same graph, draw a curve of complete saturation or zero air voids curve. The values of dry density and corresponding moisture contents for plotting the curve can be computed from the following equation. 6. Identify and report the optimum moisture content and the maximum dry density.